Assalamu alaikum. In this video, we study the definition of the Riemann integral of multivariate functions. For example, if we have a bivariate function f of x and y, we would like to define the integral. In this case, it's a double integral. So integration with respect to x and y over a closed region D on the xy plane. Okay, so this D can be of any shape. So it's a region in xy plane. So D can be of any shape, but this is a bit complicated. So in this video, we restrict ourselves to rectangular regions like this one. So this edge and this edge are parallel to the x-axis, and this edge and this edge are parallel to the y-axis. So we restrict this D to be something like this, rectangle. And in a later video, we will extend the definition to any closed regions. So let's get started. Before going into multiple integral, let us review the definition of the Riemann integral of a univariate function, say f of x, so integration from a to b dx. So what this represented was this. If we have a function of x, so, let's say this is y equal to f of x, and this is a, and this is b, so we consider this closed interval between a and b. So what this integral signifies is the area. It can be negative actually. So it's a signed area under the curve. Okay, so this is intuitively the meaning of the integral here. Now extend this idea to bivariate function. So we want to define an integral such as this in a similar manner as this Riemann integral. So what we do is this. So we have x and y-axis, and we have z-axis. So if we consider z equal to f of x and y, this represents a surface in this three-dimensional space. Okay, so let's take a cross-section along some value of y. Okay, and let's say this D is a rectangle in the xy plane, so something like this. So this is D. Okay, and this curve at this value of y may be something like, let's say, this. So we have some curve, and at this value of y, we may have something like this. Okay, and between this value and this value and this value, they may have some other values like this. So what this integral means is the volume under the surface. So it is the volume enclosed by this surface, and this rectangle. So it is something like this. Okay, so it is something like this. So this volume corresponds to this integral, intuitively speaking. But how can we calculate the volume of this solid? That's the question. Now, to answer that question, let's go back to the definition of the Riemann integral of a univariate function. Okay, this one. So how did we define this integral? So suppose this is f of x, and this is a, and say this is b. Okay, so this is how we defined this integral. First, we partition this closed interval into many small subintervals. Okay, and then we made these strips, and we approximated this area by the sum of these rectangles. Okay, so in this case, the height of this rectangle is a bit smaller than the curve itself. So if we add those rectangles, the sum of the areas of these rectangles is less than the area under the curve. Okay, so that's one thing. So let's call that sum as small s, and let's call this partition delta. Okay, so the sum of these smaller rectangles is less than or equal to the integral, the area under the curve. Okay, so the idea is we know how to calculate the area of a rectangle. So that is easy. So it's just width times the height, right? So it's easy. But we don't know how to calculate the area under the curve of an arbitrary curve. Okay, because this can be a little too complicated. So we don't know how to calculate that. But we can approximate it by rectangles. And next, we also approximate by a little bit larger rectangle. Okay, so instead of the blue rectangles, we now approximate by these red rectangles. That is, within each interval, let's take this interval, take the maximum value of the function, then make the rectangle with the height of that maximum value of the function within that interval. So the sum of these red rectangles is a bit greater than the area under the curve. So let's call this sum as capital S, delta. So delta is how we partitioned this interval. If we make this partition smaller and smaller, or finer, in other words, we refine this partition, so smaller sub-intervals, then this one becomes smaller and smaller, and this one becomes larger and larger. So by the squeeze theorem, if they converge to the same value, then that limit should be the area under the curve. So that is the idea of the Riemann integral. And we use this idea to define this double integral. Okay, so in this case, in the case of double integral, instead of these subintervals, we make smaller rectangles. So for each rectangle, we make a cuboid. Okay, and the idea is we don't know exactly how to calculate the area under this surface, but we know how to calculate the volume of this cuboid. It's easy. So it's the area, this base area times the height. So that's the volume. So if we add these volumes, that is always under the surface, then that volume should be a little bit less than this integral. And also we can take a cuboid that is a little bit higher than. So the height is the maximum value of the function or within this sub-rectangle. Then that volume is, the sum of those volumes volumes of the cuboids should be a little bit greater than this double integral. So we can have a very similar inequality like this. So let's call it like this, df of xy dx dy and volume of this. Okay, so this is like this. So this d is something like this. This is a rectangle, so we divide this into smaller pieces, and for each smaller rectangle, so let's see, suppose this is the curve surface, okay, and this is the smaller rectangle here. Then the minimum value is like this, and the maximum value is something like this. So we have two cuboids. Okay, so this is a cuboid, and we have a larger cuboid. So the sum of smaller cuboid is this, and the sum of the larger cuboid is this, and the volume under the surface is sandwiched by these two volumes. So if we make these smaller rectangles finer and finer, then this will be larger and this will be smaller. And if they converge to the same value, then that value should be the area under the surface. That is the idea of the Riemann integral of a bivariate function. Next, let's make these ideas more precise. So first, let's say we have the closed region D, that is a rectangular region actually. So on the xy plane, let's say, so this is between A and B, and this is between C and D. C and D. Okay, and we partition this region into smaller pieces like this, and smaller pieces here also. And let's name this. So this is A0, and this is A1, this is A2, and so on. And B should be equal to, let's say, AN. And so C is C0, and this one is C1, this one is C2, and so on. And D should be let's say CM. Okay, so we represent each of this smaller piece of rectangle as a Dij, okay, where this is the direct product of AI and AI plus 1 times Cj to Cj plus 1. So this is a closed interval. So this is AI, and this is AI plus 1, and this is Cj, and this is Cj plus 1. So this smaller region, closed region, is called Dij. And for each of these Dij's, we define the following quantity. Capital Mij, that is the supremum of the functional value, f of x, y, where xy is in Dij. Okay, so within this region, we search for the supremum, so the supremum value of f of x and y. So this is the lowest upper bound of f of x and y. So basically, this is something like the maximum value of f of x and y on this region. Okay, And similarly, we define lowercase mij as the infimum of the functional value f of x and y, where xy is in this region, dij. Okay, so this is the greatest lower bound of the functional value on this region. So if we define like this, then the volume of the cuboid of this shape, so this is dij, and the height is either this or this. So height is mij or maybe mij. So the volume is this times the area here is ai plus 1 minus ai times cj plus 1 minus cj, right? Because this is the region. So the area is this. Height is this for this one. And for the smaller one, the height is lowercase mij. The base area is the same. And if we take the sum over I and j, so I runs from 0 to n minus 1. J runs from 0 to m minus 1. So let's define this as uppercase s delta and lowercase s delta. Okay. By the way, this delta indicates how we partitioned this region D. Okay. Now, if we refine this partition, so that means we make a smaller partition, finer partition, by introducing more lines like this, then what would happen? So we add some lines, both vertically and horizontally, so that we have finer partition. Then let's call that partition delta prime. Okay, so delta prime is finer than delta. And the partition points of delta is also the partition points of delta prime, but not vice versa. Okay, some of the partition points are not the partition points of delta, because delta prime is a refinement of delta. So in this case, what would happen to this supremum and this infimum? Okay, now, so intuitively, you can see the situation like this. Suppose we have some function, and here, this is, let's say ai plus 1. So here in this partition, the infimum may be, let's see, infimum maybe this one is the infimum. So this is mij. And the supremum may be this one. So this is mij. Okay. And if we introduce another partition here, so now this is a new partition. Let's say this is a I prime and a I prime plus 1, a I prime plus 2, say. Okay. Then what happens to the infimum and supremum? In this case, within this partition, the supremum is this. Okay, so mi prime, j maybe prime also. So the new supremum is this one, but this one is this supremum is smaller than this supremum, right? So in general, by the way, and the supremum of the next partition, this partition, is the same as the previous one. So if we introduce a refinement of a partition, then the supremum of the function only decreases or stays the same. It will never increase. Okay, so that's one point. So that means the supremum, so m I prime j prime is less than or equal to m I j. And what about the infimum? In this case, the infimum doesn't change. Okay. And for the next one, this one, the infimum will be somewhere here. Okay, that is greater than the previous infimum. So in general, the infimum becomes larger or stays the same if we refine the partition. Okay, so that means if we have small s delta, then if we introduce refinement, then the infimum becomes larger or greater than larger or equal. So the lowercase s delta prime is the refinement of delta. We have this inequality. And similarly, we have uppercase s delta prime, so refinement. So this is supremum is less than the previous supremum. So if we keep refining the partition, then we have a similar inequality on and on. So if we are lucky, then this lower bound infimum and supremum, they will converge to the same value. So if that's the case, then in other words, the supremum of lowercase s delta. So this delta means all possible partitions. So this will only increase. So the upper bound, the lowest upper bound of this value may coincide with the greatest lower bound of this uppercase thing, infimum delta uppercase s delta. So if this is the case, then this is defined as the double integral of d. Okay, that's the definition. So if this holds, then we say this function is Riemann integrable, or just integrable. Riemann integrable, or just integrable. Okay, and so this has a finite value. In a similar manner, we can define the Riemann integral of trivariate functions like this one. So triple integral x, y, z, dx, dy, dz, and closed rectangular region. Okay. So this is not actually a rectangle, but it's a cuboid in three-dimensional space. But the idea is the same, although we cannot visualize it, because to visualize this function we need four-dimensional space, but that is not possible. But anyway, the idea is the same, and we can extend this idea to any dimensions. So in that case, for general multiple integrals, so let's say this is three-dimensional cuboid, and this is n-dimensional rectangle. So x1, x2, and xn, dx1, dx2, dxn. So just idea is the same. All right, we introduce a few important properties of integrals. So they are just the same properties as the integrals of univariate functions. So I just list them without any proof. First of all, integration is a linear operation. Integration is a linear operation. So this linearity is an important notion in mathematics. So what this means is the following. So let's say k and l are any real numbers. And suppose f functions f of xy and g of xy are integrable. Okay, so that means the Riemann integrals of these functions exist on some rectangular region D. Okay, then we have the following. Let's say, then the linear combination of these functions, k times f of xy plus L times g of xy, is also integrable. And its integral is the linear combination of the integrals of f and g. So what this means is this. So the integral of the linear combination is equal to the linear combination of the integrals. Okay, so this looks trivial and also intuitively easy to understand, because after all, the integral, dx dy here, integral is just a sum, right? It's just the limit of the Riemann sums. So, and summation is a linear operation. Okay, a sum of a linear combination is the linear combination of the sums. So the same argument applies to the integrals. So it's easy. And another important property of an integral is that integration is additive. Okay, so suppose we have a rectangular region D, which can be partitioned into mutually disjoint subsets, rectangles. Let's say dn. Then the integral over this, suppose assuming this exists, okay, then this is the integral, so this is over d and d1 dx plus the integral over d2 dy plus dot 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 So the sum of all this. So if we use the sum symbol, this is 1 to n integral over di x y dx dy. So that means, again, this is easy to understand once you realize that the integral is just a sum. Okay, so sum over this region D is the integration over this region D is the sum of the integral over this, over this, over this, over this, and so on. So it's just a sum. So this is additive. And the last property is not too trivial, but it's an important property to know. That is, continuous functions are integrable. So this means if a function is continuous on a rectangular region D, then it is integrable. So that means the Riemann integral exists. And so far, we just gave the definition of the Riemann integral, but we didn't give how to calculate these integrals explicitly. But we only know that it can be defined. And when it's defined, it has these properties. Okay, in the next video, we will show how to actually calculate these integrals.